Now let's turn our attention to storage configuration. We'll begin by exploring provisioning partitions and file systems. Then we'll move on to other more advanced storage configuration tasks such as provisioning logical volume management file systems, as well as RAID partitions and file systems. With that said, let's label this section Basic Provisioning of Partitions and File Systems. And instead of working on the local system, we're going to SSH to another Red Hat Enterprise system and provision the file system there. That system is one of the systems we've installed. So, in this section, the features include ability to provision extra storage on the fly. In other words, while the system's up and running and users are connected, and make that storage available as a mount point in the file system tree and allow users to begin writing to that space relatively quickly. And there are multiple steps involved, and we'll list those. Steps. First and foremost, you need to identify available storage. And to do so, we're going to use the fdisk command, fdisk-l, to list existing hard drives. This will give us a sense as to what has been provisioned and what has not been provisioned, and it will serve as a starting point for us to begin the provisioning process. So let's SSH over to that remote system. We'll exit this ED quota instance for the group sales, and we'll drop from root to Linux CBT, then SSH as root, since you need to be root to effect these changes on a remote system, over to the other Red Hat Enterprise system located at 75.199. It accepts us, or prompts us to accept the public key. And once we've authenticated, we'll have a shell. This server's name is Linux CBT Serv 4. If we cat the contents of etc Red Hat release, it tells us it's 5.1, major version 5, minor version 1 of the operating system. Now once there, you can enumerate the existing storage layout using df-h. This tells us what's currently allocated. There's a root file system that's about 4 gigabytes, home about 1 gigabyte, var 2 gigabytes, boot 100 megabytes, and tempfs for dev shm, as well as swap on -s revealing dev sda6 as a half a gig partition. So the first hard drive SDA is pretty full, and there isn't really any space free or much space free for provisioning storage. That's where fdisk comes into the rescue. Fdisk will enumerate the connected hard drives, whether SCSI, a TAPI, SATA, or what have you. So with that said, we'll clear screen reset the buffer, and then fdisk-l. It dumps the first hard drive, which is 8 gigabytes, roughly, with all of its partitions, including swap. It then dumps another hard drive, which is about 10, close to 11 gigabytes, which is unpartitioned. You can tell that it's unpartitioned because fdisk returns the fact that dev SDB doesn't contain a valid partition table, so it has no indication on its drive as to the layout of the partition or partitions. So it has no partition layout, no partition table. So fdisk is the program that we want to use to create partitions. Optionally, we may use parted. Either or will do. So we've identified available storage. This returns connected storage and tells us what we may use for storage, and that may include free space on an existing disk. So fdisk-l will tell us if there's any free space. For example, it tells you the total number of cylinders, 1044, and if you follow the cylinders 1 through 13 for the first 3 partitions, which terminates at 796, the extended occupies 797 through 1044, and we have allocated up to the 992nd cylinder, leaving us between 993 and 1044 for allocation. So there really isn't much space available, which is why we want to focus on SDB, another connected hard drive. So with that said, we'll use the fdisk command followed by the path to the hard drive. So the next step is to create partitions on desired hard drive. And to do so, we'll execute fdisk followed by dev-sdb for the second SCSI hard drive. In this case, it happens to be a SATA drive. So interacts with dev-sdb drive as opposed to dev-sdb, dev-sda that is, or dev-sdc or some other drive. So it's fdisk dev-sdb. This propels us into fdisk, returns some useful information, and if you need help you press M. However, generally you'll press P to print the partition table, and if there is none, which that is the case for us, we can create one by using N to add a new partition. So our first step is, after entering, our next step is to execute N to add a new partition. Now we know that the hard drive is about 11 gigs, 10 to 11 gigabytes. So we should determine how much space we'd like to allocate for our new mount point. We haven't determined what the mount point will be in the Linux file system tree, but that's unimportant right now. What's important is how much space we'd like to use of the roughly 11 gigabytes. So supposing we need an extra 4 gigabytes of storage. We'll indicate N to create a new partition. We need to determine whether or not it's primary or extended. As we've mentioned, when creating file systems on a PC, partitions on a PC, you need to always bear in mind that there's a limitation of 4 primary partitions, or optionally 3 primary and 1 extended, or up to 3 primary and 1 extended. Within the extended partition, you can create a large number of logical partitions to further divide your storage. So since this is the first partition, we'll make it a primary partition. We then need to pick a number. Well, since it is again the first partition, we'll default to number 1. You also need to determine the cylinder, the first cylinder. You can create a partition using fdisk anywhere in the disk. It doesn't need to be at the beginning of the disk. You could start, let's say, at cylinder 100 and stop at cylinder 199 if you'd like. We'll start with 1, that's the default, and then you indicate the size of the partition using plus followed by one of the following: megabytes, gigabytes, kilobytes, so on and so forth. Now we want this to be 4 gigabytes, so we could indicate plus 4096 megabytes, which is equivalent to 4 gigabytes, or plus 4G. Either or will do. Since we know that the exact number of megabytes is 4096, since we are moving in increments based on base 2, so 1024 would be 1 gigabyte, 2048 would be 2, and 4096 would be 4, we'll indicate plus 4096 megabytes. When you specify the total storage using this format, fdisk handles the allocation of the cylinders, so it performs the math to determine the last cylinder that should be used to achieve 4 gigabytes worth of storage. Now if we reprint the partition table, you'll see that there's a new partition, SDB1. The hard drive is SDB. The first partition is SDB1. So new, next step is we need to indicate that it's primary or extended, followed by 1 for start cylinder, followed by, in our case, plus 4096M to indicate 4 gigabytes out of the 10 to 11 that are available. But these changes have not been written to the disk just yet. These are just temporary interim changes. In order to commit the changes to the disk, execute M for help, and you'll see that writes the changes to the hard drive. So W updates the partition table. You may optionally create additional partitions, but we'll do that later on when we show you how to create swap partitions and swap files or swap file systems based on files and partitions. So again, we've created a new partition, and by default fdisk defaults to type Linux. type 83 or ID83, which is type Linux. This is the type of file system that we need, or type of partition that we need to create a standard Linux file system such as Riser, ext2, or ext3. However, when creating, let's say, RAID or LVM type partitions, you need to indicate those types of partitions. You can change the type of a partition by indicating option T. When you do so, you can also indicate L to list the different available codes. Here are all of the different types of partitions supported by the Linux kernel. Everything from old-fashioned FAT12 to AIX to Solaris, Amoeba. Virtually every computer and file system partition type that's been invented is supported by Linux. 83, however, represents the standard Linux partition type, whereas there are other types available, such as 82 for Linux swap, which we'll see in the subsequent section when we focus on Linux swap partitions. Linux LVM is type 8E. NTF 86, 87, OS2, Linux Extended 85, and so on. So there are different types available, and you just need to go through this list to select the type. You can print the type, take a look at the type, make changes, but be careful what you set, because it may take effect permanently. So for example, if you were to type 83, it would change the partition type. Now we've exited. Let's return into the partition layout and then print, and you see that the changes are lost. We Control-C just to show you that unless you've written the changes to the partition table, they're lost. So again, we need to redefine the partition indicating new, the fact that it's primary, the first, beginning with the first cylinder, and plus 4096 megabytes or 4 gigabytes. We reprinted its type Linux, and again, to save the changes, Option W to write the table to the disk or to update the partition table. So let's move forward. You may also delete partition if you'd like by using the D option. So this writes to the hard drive, and if all goes well, we'll be able to create a file system on the hard drive. Sometimes there are problems syncing to the disk, especially for disks that are currently in use. So for example, fdisk-L, if we attempted to update the first disk, SDA, by creating a new partition between the cylinders 993 and 1044, sometimes with a running system, you'll be unable to do so unless you use the part probe utility. The part probe utility forces changes when you indicate the partition. So note, use part probe followed by the partition, which is usually dev / and the identifier such as SDB1, to force a write to a hard drive's partition table on a running system. This will ensure that you don't have to reboot to commit the changes when using fdisk, as was the case with older versions of Linux. But in this case, we don't have a problem because we saw that the disks were synced, or the disk was synced with no problems. So that tells us that the partition's available, and when we executed fdisk-L, we saw on the second hard drive dev SDB1. So now the partition's available, but this is known as a raw partition. So we should just note that. Note, fdisk creates raw partitions, which works for some applications such as Oracle, and perhaps even MySQL, which provides support for accessing raw partitions. In order to make this partition available to the user community, however, we need to overlay it with a file system such as ext2, 3, RiserFS, JFS, XFS, or one of the many supported file systems. Otherwise, the file system will not be available. In other words, in order to make it show up when we use df-h in the list of available file systems, we need to overlay a file system. So step 3 is to overlay or format the raw partition with a file system. And with Red Hat Enterprise Linux, the standard file system is ext2, or optionally ext3, which is a variant of ext2 with simply journaling turned on to increase availability and recoverability of your storage volume. So to do so, we'll use the make2fs command. The make2fs command creates a file system on the hard drive. We also want it to be an ext3 file system. So oddly enough, you still use the make2fs command, not make3fs, but you simply indicate the J option, and that's lowercase j, to indicate that you'd like to turn on journaling, which renders the partition an ext3 file system. So that's going to be devsdb1, first partition on the second SCSI hard drive, which is really a SATA hard drive, but it appears using the SCSI nomenclature, since SATA is a cross between old-fashioned IDE ATAPI and SCSI in terms of performance, scalability, so on and so forth. So this will overlay the file system and write the inodes. So overlay, format the raw partition with the file system. This will write inodes to partition. Once we've written the inodes, once make2fs has calculated the inodes and has written it to SDB1, the raw partition, the partition then becomes available for mounting, which will be step 4. And then step 5 is to simply ensure that when the system boots, the partition becomes available. So once we've created a file system, we can determine where we'd like to mount it within the Linux file system hierarchy. Once we've made that determination, we'll update etcfs tabs so that when the system's rebooted, the file system is made available to the user community. So with that said, let's go ahead and make 2fs on devsdb1. There you see the inodes were written to the drive, the journal is being created, and the file system is being properly applied to devsdb1. This tells us that it's finished, and the file system will be automatically checked every 30 mounts or 180 days, whichever comes first. But you can always use the tune2fs command to check the file system to be sure that it hasn't lost any data or has any orphans or so on and so forth. In other words, ensuring the integrity of your files. With that said, we can now mount the file system. Let's move to step 4. Mount the file system in the Linux hierarchy. This is an easy step. By default, mount will recognize certain types of file systems such as NFS, as well as ext2 and ext3. So there's no need to indicate mount type ext3, for example. You can simply indicate mount, followed by the raw partition location, dev sdb1, followed by the place within the file system hierarchy that you'd like to have it mounted. Now this depends on what you want the storage to be used for. So you need to take a look at your root and see what's missing or what you'd like to allocate the storage for. We've pretty much got everything available, from opt to etc to var, you name it, it's available. So if we wanted to create, let's say, a new home mount point, home1, that we'll use for a set of our users, that's a good idea. To do so, make directory /home, make it first. Otherwise, home1 that is, otherwise you'll be unable to mount to it. So we're going to mount devsdb1 to home1, but before we mount, we make directory /home1, and then if it succeeds, we mount. Let's go ahead and try that. We'll echo the exit status. It's 0, which now means if we execute mount, we'll see home1 is mounted and is available. Here it is, devsdb1, home1, and it's mounted with the default options of read-write, as are the other ext3 file systems. So 2, or step 2 in section 4, is to execute mount. This will reveal, or let's indicate mount or df-h. Either will reveal that devsdb1 is mounted. if all went well, of course. And as we can see, things did go well. Let's follow that up with df-h. Now we see Home 1 is available. It's almost 4 gigabytes, of which 72 megabytes are in use. You might be wondering what's using the space. There's overhead required for every file system, whether NTFS within Windows, ext2 or 3, or RiserFS within Linux. There's always file system overhead to maintain it, such as journaling in this case, space for lost and found, so on and so forth. So there's always a small percentage dedicated to managing the file system. But we have the bulk of the file system available for our usage. So now when we look at LSLTR, using LSLTR Home 1, we'll see that there's a lost plus found entry. Let's just copy and paste this and just note that for each distinct file system there's a lost plus found directory. Note, lost plus found is created for each distinct file system, and it stores orphaned items that are no longer linked or owned by anyone or that have been discarded. It isn't a recycle bin, so you cannot recover items that you have deleted. That feature isn't in there. However, it will serve as a place to store orphaned items that cannot be resolved to users on your system. So now we've got this new file system. We can create items in it. We'll sequence 1 million. Home 1, test.txt, this will create a file in it. And so long as the permissions, if we LSLD Home 1, are set accordingly for users, they'll be able to interact with the directory. For example, the home directory has similar permissions, owned by root and root, with permissions 755. But if you wanted to set up a user or modify an existing user with a directory beneath Home 1, that's perfectly fine as well. For example, you could use usermod to copy a user's home directory. So if you remember usermod, and we mentioned that these commands always come back, we always use them. We could use usermod to move a user's home directory, providing we're not in it in the directory. Let's just exit one of these to be sure that we're not in it. But you could usermod m student1, but you need to indicate with the D option the new home for the user, which may be Home 1, Student 1, for example, for the user Student 1. And in this case, the user doesn't exist on this remote system. Let's go ahead and user add and create the user fresh. User add D, Home 1, Student 1, the name of the user Student 1. Since we're on a remote server here, it's part of the confusion when you set up users or interact with Linux systems in a shell environment. You never really know where you are on the system unless you pay attention to the prompt. I am root at Linux CBT Serve 4 as opposed to Linux CBT Serve 1, which is the host system. So let's take a look at what's currently set up. If we LSLTR Home 1, we'll see that the user add process has created a Student1 directory in the Home 1, and as you can see, we threw it off. Let's user del help. We threw it off. We indicated Student1. We'll remove the items for Student1. And now let's LSLTR Home 1, and it's gone. You may be wondering, how did it resolve Student1 to Student1 without a T? Because of the etc password entry. Now let's recreate the user. So we'll user add Home Student1, Home 1 Student1 for Student1. And now when we LSLTR Home 1, we see the directory has been created by the user add process. In it, we'll find, if we turn on the hidden option, bash files, which are copied automatically from etc skel. And we'll LSLTR etc skel with the A option turned on, not cat. These are the options that are copied automatically into the user's home directory. Now if we use usermod to move the user's home directory, let's say to Home Student1, then that would work as well. So for example, usermod Home Student1, move Student1, this takes care of moving the user out of home 1 into home, just like that. And now we can move the user back if we'd like. So it's user mod D home 1 student 1. Now the user will be moved out of home into home 1. So using user mod, you can move the user's tree and preserve permissions about the various mount points. So now we have storage. This user differs because this user will be parked at the home 1 mount point. But we've yet to do one important thing, and that is to set up the home 1 mount point so that when the system reboots, it's auto-mounted. So the fifth step, aside from all the playing around we've been doing with user mod and user del, user add, is to configure /home1 to auto-mount when the system boots into various run levels. To do so, we'll nano etcfs tab and copy the home entry and modify. So we'll copy and modify the home entry to suit our needs. And that's the /home entry, of course. Let's take a look from our shell. We'll reset the buffer and then nano etcfs tab, our file system table file. Here's a label for home. We want to duplicate this, so we'll just Control K and Control U twice, and the new label will be for home 1. We'll bring this back up, keep everything on the same line, otherwise you'll have problems booting, or at least have problems at that point when the file system attempts to boot. And don't forget, like we did earlier, if you want quota support, and now's your opportunity, turn it on. So we'll indicate user quota as well as group quota support, just in case. And bring everything back onto one line. So now home 1 will be automatically mounted whenever the system boots. And ditto for the home partition. If you want to enable or impose limitations on home as well, just go ahead and update it with user quota and group quota support. So let's indicate user quota, comma group quota support. Now both file systems will be able to support quotas. So now we've set up our file system to properly mount whenever we reboot the system. And since this is a remote system, we can reboot it and then check in with it to determine whether or not it's actually worked. Now there are additional utilities that you may use, GUI as well as TEX. For example, if parted is installed, this is another utility. Parted can be used to automatically create file system partitions. When you execute parted, you indicate a partition, otherwise it defaults to no partition. You execute help, and then you'll see how to set as well as select a given device. You can also print to display a partitions table, but we're not in a partition, so you'd have to select it. So select, for example, dev SDB, and then print dev SDB's table where you'll see the lone partition, the fact that it starts here and ends here, and that it's primary and ext3. So this is yet another utility that can be used. Parted also has a unique ability to allow you to assign a file system ext2 or 3 from within its interface. It automatically takes care of it for you. So this is another tool that's useful that will allow you to manipulate partitions relatively easily. Now at this stage what we should do is reboot the remote system. It's currently in run level number 3. We should reboot it and then confirm that the file system has been brought up for us. Now while it's being rebooted, we'll recap the steps required to create a partition, an ext3 or 2-base partition. They include the fact that you need to identify available storage. So you use fdisk-l, or you may use parted with the appropriate partition. fdisk-l tells you what's available, what's connected, and what's available. You can tell what's available because even on our local system, for example, let's find a root shell, just to recap that process. We use this third shell over here. and it's been closed, so we'll SU in. So even on the local system, when we execute fdisk-l, it tells you the connected hard drives. It also tells you the total number of cylinders, 16,065. So all you need to do, or in this case 4,863, this is the multiplication, the value of each cylinder. So 4,863. So all you need to do is look at the layout of the partitions to see whether or not any of the partitions make it up to the end or the last cylinder, or close to the last cylinder. In the case of this computer, yes, 14 through 4863 represents an LVM volume. So in this regard, we can't create any additional file systems. However, in the case of the system, the remote system that we rebooted, it had a spare hard drive. So we were able to lay out file systems on that spare hard drive. It also had space on the primary hard drive. This system's booked. There's no space, but the remote system has space. So you need to identify storage. Use fdisk to do that. Then you create partitions using fdisk, followed by the hard drive that you'd like to operate on. If it's primary, you indicate primary, but you always indicate M to indicate that you'd like to add a new partition. If you'd like to delete a partition, then just press D and you'll delete it. You determine the start cylinder. For the subsequent partition that we'll create for swap, we'll start where the cylinder is free, so at the first free cylinder, and then increment it to the size of the swap that we'd like to allocate. Save the changes using write. We didn't indicate that, so step F, W, to write the changes to the disk. And if there are problems syncing the disk, then use part probe and the partition. In the case of the partition we recently set up, that would be dev SDB1. That forces a write to the hard drive's partition table on a running system. Worst case scenario, if it doesn't work, reboot your system and it will work. You then create a file system using make2fs or riserfs, make riserfs. You create the file system. For ext3, use lowercase j followed by the partition number, beneath the dev tree, of course. Once you've created the file system, you're free to make a directory and mount it. Once you've proven that you can write to it, interact with it, and all looks well, update your etcfs tab so that when the system reboots, the mount point is available automatically. And that's really all there is to provisioning a simple ext3 or 2 file system. If you wanted ext2, which means ext3 or ext2 meaning no journaling, then drop this lowercase j option. That'll create an ext2 file system instead of an ext3 file system. And by now the file system should be up, so let's reconnect. And there it's prompting us. df-h, and there you see home 1. System has been up for 3 minutes. So home 1's mounted, and that means the data are accessible. Now if you encounter problems remounting using a label, consider changing your label to the dev location, such as dev SDB1, in your etcfs tab file. So for example, let's nano etcfs tab. We've got label home 1. Sometimes the kernel throws an error because it's unable to find a disk with a label. So unless it's labeled home 1, it might give an error when you boot. So change this. In our case, it hasn't given an error, but change this to dev SDB1, and you should have no problem mounting it. And just ensure that your syntax is proper for user and group quota, and the file system will come up whenever you boot your system. So that's a basic ext3 file system. Next, we'll focus on swap file systems.